Okay, let's do some more problems on constraint optimization. So what's the algorithm? Understand the objective function, understand the constraint, construct a new Lagrange function, capital F, with the help of small f, objective function, and phi or a z or whatever, the constraint function. So we construct capital F as f of x, y, z plus lambda times pi of x, y, z, and we impose that stationary points condition on that. That will yield you three equations. Those three equations intact with the constraint solve, you get a optimized point. Plug in, you get the optimized solution, right? So let's do the example here. Find the maximum and minimum distances of the point 3, 4, 12 from the sphere x square plus y square plus z square equal to 4. We don't know what is that point. Let x, y, z be any point on the sphere, right? Then the distance from OP equal to x minus 3 whole square plus y minus 4 whole square plus z minus 12 whole square, right? Let it be f of x, y, z. We have to find the maximum and minimum of f of x, y, z subject to the condition phi of x, y, z equal to x square plus y square plus z square minus 4 equal to 0. With respect to that sphere, we have to find the distance, no, from the point 3, 4, 12. Let's construct a new Lagrange function. Capital F of x, y, z equal to small f of x, y, z plus lambda times phi of x, y, z. That equal to x minus 3 whole square plus y minus 4 whole square plus z minus 12 whole square plus lambda times x square plus y square plus z square minus 4. Then dou f by dou x equal to 2 times x minus 3 plus 2 lambda x, and dou f by dou y equal to 2 times y minus 4 plus 2 lambda y. Dou f by dou z equal to 2 times z minus 12 plus 2 lambda z. Dou f by dou x equal to 0, dou f by dou y equal to 0, and dou f by dou z equal to 0 implies x minus 3 plus lambda x equal to 0, y minus 4 plus lambda y equal to 0, z minus 12 plus lambda z equal to 0. Pull out lambda from that. So lambda equal to x minus 3 by x from the first one, y minus 4 by y minus y rather from second one, and z minus 12 by minus z from the third one. All the three are equal. Okay, right. Now, plug into the constraint there, right? Then go through the algebra there. We know that the constraint is x plus square plus y square plus z square equal to 4. Solve that. And finally, you get root f equal to 12, 14. Okay. Since the maximum is 14 and minimum is 12. Next one. Show that the rectangular solid of maximum volume that can be inscribed in a sphere is a cube. Let 2x, 2y, 2z. I've taken 2x for sake of convenience, which you can understand just ahead. Right? 2x, 2y, 2z be the length, breadth, and height of a rectangular solid, so that its volume equal to V equal to 8xyz. Let capital R be the radius of the sphere, so that x square plus y square plus z square equal to r square. That is a sphere, right? And its volume is fixed, V, right? Now, what is the volume? 8xyz. What is the constraint? X square plus y square plus z square minus r square equal to 0, because that has to be fitted into a sphere. No, let us construct the Lagrange function, capital F of xyz equal to 8xyz plus lambda times x square plus y square plus z square minus r square. Dou f by dou x equal to 0 implies 8yz plus 2x lambda equal to 0. Dou f by dou y equal to 0 implies 8zx plus 2y lambda equal to 0, and dou f by dou z equal to 0 implies 8xy plus 2z lambda equal to 0. Pull out the lambda, all the three should be equal, right? That implies x equal to y equal to z, which is nothing but a cube. Okay, right. Next one. If u equal to a cube x square plus b cube y square plus c cube z square, where x power minus 1 plus y power minus 1 plus z power minus 1 equal to 1. Show that the stationary value of u is given by x equal to sigma a by a, y equal to sigma a by b, z equal to sigma a by c. Now, let u equal to f of x y z, that equal to a cube x square plus b cube y square plus c cube z square. What is the constraint? X power minus 1, y power minus 1, and z power minus 1 equal to 1. Mean 1 by x plus 1 by y plus 1 by z equal to 1. Okay. Now, let's construct the Lagrange function. Capital F of xyz equal to small f of xyz plus lambda times phi of xyz, that equal to a cube x square plus b cube y square plus c cube z square plus lambda times 1 by x plus 1 by y plus 1 by z minus 1. Now, dou f by dou x equal to 0, dou f by dou y equal to 0, and dou f by dou z equal to 0 implies dou f by dou x equal to 0 implies 2a cube x square minus lambda by x square equal to 0. Now, dou f by dou y equal to 0 implies 2b cube y minus lambda by y square equal to 0. Dou f by dou z equal to 0 implies 2c cube z minus lambda by z square equal to 0. Right? Which implies 2a cube x cube equal to lambda, 2b cube y cube equal to lambda, and 2c cube z cube equal to lambda. Which implies 2a cube x cube equal to b cube y cube equal to c cube z cube. Right? Now, let ax plus b equal to by equal to cz equal to k, say, then x equal to k by a, y equal to k by b plus comma z equal to k by c. Substituting these in the constraint, 1 by x plus 1 by y plus 1 by z equal to 1, we get k equal to a plus b plus c. Right? Hence, the stationary value of u is given by x equal to sigma a by a and y equal to sigma a by b, and z equal to sigma a by c. Sigma a, I mean a plus b plus c. Okay. Yeah. You can go through. You can go through. Now you don't need a teacher here. You can go through, understand the problem over there. Look, dou f by dou x equal to 8xyz plus lambda times 2x by a square. Similarly, you just go through, you can understand. Okay, that's how we solve problems with constraints and problem without constraints. Sometimes a problem with constraints can be converted into problem without constraints, but problem with constraints is wise to deal with Lagrangian multipliers method.